and then after that we just start reviewing. So the final exam is not cumulative. So work on look at homework problems that I've assigned from sections, with everything after the second lecture basically. So chapters 6, 7, and 8, topics from those sections. So that's basically joint distributions, sums of independent random variables, conditional distributions, properties of expectation, variance, covariance, correlation, and then conditional expectation as well, and then moment generating functions, and then the starting chapter.
So today we're starting chapter 8.
Yeah, finishing up the moment generating functions, and we start with central theorem.
Is the exam going to be the whole 2 hours, or is it going to be?
Yeah, that's it. I mean, I'm guessing. Right, regular question. I'm guessing we'd be able to finish the exam in an hour and a half. But I will give you a whole 2 hours.
Thank you.
In case you want to share my confidence.
Can you go through that list one more time, just to make sure it'll be?
I mean, we will go over that again, I mean, next week, but, so it's chapter 6. So chapter 6 includes joint distributions, independence, sums of independent random variables, conditional probabilities.
And what?
Conditional distribution.
You should write this down.
So look at these topics, joint distributions, this whole idea of independence. Then we have sums of independent random variables. And then I have conditional distributions. That's chapter 6. In chapter 7, you have conditional expectation. We have properties of expectation. And then things like variance, covariance, correlation. Variance, covariance, correlation, yeah, that's basically it. Then moment generating functions. Moment generating functions. And then chapter 8, you will have the central limit theorem. And the Chebyshev's inequality. So that I'll talk about on Monday. So you can start making a list of formulas and working on that.
Can you say that word,
Chebyshev. Continuing with moment generating functions. So the moment generating function for a random variable x is a function of t, which is defined as the expectation of e to the tx. And last class we computed the moment generating function for different random variables. So today I'm going to mention two important properties of moment generating function. I mentioned them last class, but we're going to write them down today. One of them is that the moment generating function of sums of independent sums of independent random variables is the product of their individual moment generating functions. So here's the statement of this mathematical statement. If x1, x2, xn are independent random variables, when I look at the moment generating function of this new random variable, which is the sum of x1, x2 up to xn and t, is just going to be m of x1 at time t times m of x2 at time t times m of xn. And the proof is really simple, so we might as well just do the proof here. Suppose, let's just do it for x and y. Are independent. So just for n equals 2 case, and you can extend it to larger n. Let's look at the moment generating function of x plus y. That is just, by definition, is the expectation of e to the t times this random variable x plus y. That's just the expectation of e to the tx plus ty, which you can write as e to the tx and e to the ty. And now, by independence, we know that if I have the expectation of a function of x times a function of y, it just becomes. And this is by independence. So this, from here to here, that's from independence. And if you look at this, that's just the definition of the moment generating function of x at t, and this is the moment generating function of y. So for the case where n is 2, we prove that the moment generating function of the sum of two independent random variables is the product of their individual moment generating functions. Oh yes, I think I had to collect homework.
What's central limit theorem? Speaking of homework, will we have one more assignment?
Yeah.
Due Wednesday. And the following Monday, the week of the final exam, definitely no class? Or maybe class? Or...
There's class.
Oh, what?
It's Tuesday that's the study day.
Oh, okay.
So you have class, but I mean, I'll cancel it.
Oh, I thought you said tonight and one more week.
Right, I forgot.
That was just like another question review day.
Right, yeah.
Monday's question day?
That's just the day where she gives us the answers to the questions in the final.
That would be awesome.
I still would find a way to fail.
Now we're gonna do it all together. She's like, no.
Practice final.
One thing that we can answer.
Oh, take home exam.
Oh.
You want to take home exam?
A take home exam?
I think that would be even worse because you'd make it really hard.
Yeah.
No.
If you can make it just a little bit harder.
No. What do you shush?
What, take home is good?
Yes.
Wait, how much do I trust you people?
A lot.
I mean, we do have things like MAT-5700. Okay, I'll think about that. Oh, no, I shouldn't get your hopes up. No.
No, think about it. Think about it. I like that.
The exam is on April 24th and in class. Okay.
Just think about it.
Yeah, I like thinking about it better.
Okay, the moment generating function. Okay, so this is this other property that's which makes moment generating function very useful, and it says that the moment generating function uniquely determines the distribution. That is, if mx exists, finite. So region about t equals 0, then distribution of n is. So, I mean, if the momentary function is just not defined anywhere than, except at 0, then that doesn't help us at all. But if you have a momentary function that's defined at least in some interval, from 0 to some point, then the distribution of x is uniquely determined by that function.
Is that what that notation means? This distribution? It's like
Yeah,
one?
distribution.
Okay.
Yeah. I've been using it for the last 2 months at least, since we used the word distribution.
And for the last 2 months, I've been looking up there like, what? I didn't want to ask because
You should have just asked.
yeah, but you're so unfriendly when we ask questions. Just kidding.
Now we're really not gonna have take-home. Way to go.
Yeah.
If I keep going like this, we won't have an exam at all. Wait a minute.
She might kick you out of class if you keep going like that.
That's beginning to sound like a good idea, huh? Okay, 1/2 10th of T1. So if I tell you that I have a random variable and I've calculated this moment generating function and I get this, when you look at this, you should be able to say that, okay, this looks like the moment generating function. Actually, just from the moment generating function, you can tell what the distribution of x is. Okay. So in this form, maybe it doesn't look that familiar, but let's just manipulate this slightly, and we see that we can write it in a form where we recognize it as a moment generating function that we've calculated. All right. So take 1/2 inside because they both reach to the same power. So I can write it as e to the t plus 2. So this is 1/2 e to the t plus 1 minus 1/2. And doesn't this look like p e to the t plus 1 minus p? And that is the moment generating function of binomial np, random variable. Therefore, x must be binomial with n equals 10 and p equals 1. So if we know the moment generating function is this, then we know that x, this is the only possible distribution it can have. So it cannot have any other distribution. That's what I mean when I say that it's uniquely determined by the moment generating function. So two different distributions cannot give you the same moment generating function. So if you can identify the moment generating function as corresponding to a certain distribution, you know what distribution x has. So this makes the following problems easy. In one of the sections, we looked at the distribution of sums of independent random variables, right? And it was complicated because to find the distribution of sum of x plus y, we first calculated the distribution function and then we took the derivative to calculate the density. But now, it's not in all cases, but in some cases, let's look at this problem. If x and y are independent binomial np, random variables respectively, find homogeneous function of x plus y. Or is the distribution of x plus y. Or actually, let me say this. If that x plus y is binomial, plus parameter n plus n, alright, so if you hadn't learned moment generated functions, what you would have done is you would try to calculate the distribution function of x plus y first, take the derivative, and check if the density is the same as what we expect the density of our binomial random variable to be. Okay. So, but we have an easier method here, and that is, and I didn't do the sum of independent binomials of this form under this distribution, under this section, because it's a little complicated using the method of distribution. All right, so let's just look at this. So what all we need to do for this proof is, let me see. Now that we know this property of moment generating functions, all we need to do is show that the moment generating function of x plus y has the form of a binomial moment generating function of a binomial random variable with these parameters. Okay? And if we do that, we're done. All right, so let's start by calculating the moment generating function of x plus y. By the first property, I know that if x and y are independent, this is just mx of t times my of t by independence. And my first property basically said that if x and y are independent, the moment generating function of the sum is the product of the moment generating functions. What is the moment generating function of x? X is binomial n to p, so the moment generating function has the form p e to the t plus 1 minus p to the n. This has the form p e to the t plus 1 minus p to the n. At the same number raised to different exponents, so I can just add the exponents, just add. And this is just the moment generating function of binomial with these parameters. So we're done. So if you want, you can say this is the moment generating function of distributed random variable. So it makes these proofs really easy. When you have independence, you can just multiply the moment generating functions, and then if you see a moment generating function that you recognize, then you know exactly what the distribution is. So how about for Poisson? If I have independent Poisson random variables, what is the distribution of the sum of independent Poisson random variables? So this, I think we've done when we looked at the distribution of the sum of independent Poisson random variables. Some lambda lambda 1 and y is Poisson. Independent. This is the x plus a lambda independent. So let's figure out what the distribution of x plus y is. Will it be of a form that we recognize? So what is the distribution for, what's the moment generating function for Poisson? So the first step is by independence. We know it's just going to represent the product of that. And in croissant, we know that what is it? It's lambda e to the just e to lambda. So this is going to be e to the lambda 1, e to the t minus 1. This is e to the lambda 2, e to the t minus 1. And again, we can put these together. You get e to the lambda 1 plus lambda 2 times e to the t minus 1. So this looks exactly like the moment generating function of a Poisson random variable with this as a parameter. Therefore, x plus 1 is Poisson. So these proofs now are really easy. The sums of independent random variables, you can get their distribution right away. All you need to do is know what the moment generating functions of these have to be and recognize the moment generating function that you get at the end. Similarly, let's do for normal. And I think for normal distribution, I just stated that the sum of two independent normals were going to be normally distributed. So here we have an easy proof for that. So let's take if x is normal, mu1 sigma 1 squared, and y is normal, mu2 sigma 2 squared, show that x plus y is normal mu1 equals mu2 sigma 1 squared plus sigma 2 squared. The means get added, the variances get added. So, proof, that is really simple. Let's calculate the moment generating function of x plus y.
They're independent, right?
Yeah. Oh, yes, good. This is if x is independent. Yeah. Now, if they're not independent, you can still calculate it, but what you would need to calculate, you will need to know something called the joint moment generating function. And we're not going to get into that. If you're interested, you could read that up, it's in the book. But let's just stick with independence, because with independence we have that nice property. And if they're not independent, you don't get you get the sum to be normal, but there's something different about this. Well, yeah, the covariance structure is a little different. It's going to be Gaussian, but you have some kind of interaction between the x and y terms. All right. So only in the case of normal, these add. Okay, what would this be if they were not independent? Something that we did last week. This is going to be the variance of x plus y.
Yeah.
And what would the variance of x plus y, this is some property that you must have used for your homework.
I
If x and
remember.
y are independent, just be variance of x plus variance of y. If they're not independent, it is, you will have some covariance term. You remember this formula, variance of summation I equals 1 to xi. You did need to use this formula on your homework, so if you didn't use it, then you're getting something wrong. Or no, I think you guys just had covariance, so that should be fine. But all right, so this is going to be variance of x plus variance of y, covariance of x and y. Because this was the summation variance of xi plus plus 2 covariance, this is j covariance xi, xj, right? That was your formula. All right, so you don't get something as simple as this. You get sigma 1 squared plus sigma 2 squared plus 2, and you would have to calculate the covariance of x and y. So, that will be something complicated, and I haven't told you what it means for x and y to be jointly normally distributed. So, but it's something that it's good to know that I can ask you about. I mean, I will not ask you in the exam, but there are situations where you look at the sum of two normal distributions, and they need not be independent. So independence makes a lot of things easy. Alright, so this is my independence. What was the moment generating function for normal distributions? This is e to the mu1 t plus 1/2 sigma 1 squared t squared. This is e to the mu2 t plus 1/2 sigma 2 squared t squared. And this becomes such a simple proof for showing that x plus y is also normally distributed with the parameters that we get. So therefore this x plus y is normally distributed. The mean has to be here, mu1 plus mu2. The variance, you normally have variance, the variance term here, and that variance term is sigma 1 squared plus sigma 2 squared.
Where did the 1/2?
Oh, sorry, 1/2, I should write that here also. No, I have written the book.
Yeah, you have. I'm just asking where it came from, please.
That's in the moment generating function for if x is normal. This is your moment generating function for normal. So it's in the formula for